start, let me ask once again. My screen is visible and am I audible?
Yes, sir.
Yes, sir.
Audible.
Okay,
Yes,
okay.
sir.
Okay, thank you. Okay. So in today's session, I will first introduce what is a time series, what is time series forecasting. Then I will give you the motivation for time series forecasting, and I will specifically emphasize on the motivation for a material engineering. Then I will go through time series forecasting using optimized deep learning models. Then I will discuss some of the hybrid time series forecasting methods using deep learning models. Then I will go through fuzzy time series forecasting using optimized deep learning models using various fuzzy sets. So before going through this, let us exactly know what exactly a time series is. A time series is a set of observations of the same variable measured sequentially through time. So the variable may be temperature. So if I want to measure the temperature at NIT Raulkela in a daily basis. So from the last 2 years, if I am measuring the daily temperature at NIT Raulkela, then I will get a daily temperature time series. Similarly, the variable can be anything. It can be the material characteristics that change over time, right? It can be the number of passengers traveling in an airline, number of passengers traveling in a train. It can be anything. Okay. So the time series can be discrete time series or it can be a continuous time series. In discrete time series, the measurements are done at discrete instance of time. For example, suppose I want to measure how many passengers are traveling in a specific airline. So you see, in every travel, we will count the number of passengers. So it gives you a discrete time series. Whereas if I want to measure the EEG signals of a person, then it will give you a continuous time series. However, all of you know that nothing is continuous in this universe. If the time space is so small, then we are thinking it as continuous. So every continuous time series can be converted into discrete time series by following discretization method or random sampling at regular intervals. Then the time series forecasting methods can be applied. The time series may be crisp value or it may be fuzzy value. Crisp value means suppose we are measuring the temperature at an outdoor. Let's say the temperature are 40 degrees centigrade, 35 degrees centigrade, 28.9 degrees centigrade, 25.8 degrees centigrade. So if the measurements are from a real domain, then it is called as a crisp time series. Whereas if instead of measuring the actual temperature, if I want to measure only, let's say very low temperature, medium temperature, high temperature, very high temperature, if I will use linguistic terms to denote a particular variable, then that is called as a fuzzy time series. However, as most of the observations are measured in crisp domain, we can convert a crisp time series into fuzzy time series by using a fuzzification method. Then we can operate in the fuzzy domain. Then again, we will come back to the crisp domain by using a defuzzification method. So before going through all these time series forecasting methods, let me go through the basics of time series, that is the components of a time series. So a time series may have four components. One is trend, seasonal, cyclical, and irregular. So here the important thing is I have told you that may have these four components. So any of the components might be absent also. So let us understand what exactly a trend is. So trend is a pattern in data that shows the movement of a series to relatively higher or lower values over a long period of time. For example, suppose we want to measure the number of passengers traveling in an airline from 1950 to let's say 1970. So usually you see that the number of passengers will be increasing every year. For example, I want to take a time series, electricity load time series. So electricity load will definitely increase in next year, and in the coming years. So here we are having an increasing trend. If the time series increases over a longer period of time, then that is called as trend. If it increases, it is an increasing trend. If it decreases, then it is a decreasing trend. Suppose we are measuring a time series with the number of child deaths from 1970 to till 2015. So you see the medical facility from 1970 to nowadays is very advanced. So usually the number of child deaths will going to definitely decrease. So here we will get a decreasing value for a longer period of time. Then that time series is a decreasing trend, right? So trend may be increasing or it may be decreasing. Next is seasonal component. Seasonality, as its name suggests, refers to the seasonal characteristics of the time series data. Seasonal characteristics means, suppose we want to measure the temperature in a year. So you know that in winter, the temperature is low, and in summer, the temperature is high. It is true for every year, right? So it has some calendar effect. For example, we want to measure the mango price at a particular city. So during the mango season, the price of the mango will be low, and in the non-seasonal days, the price of the mango will be high. It is applicable to all kinds of fruits and all kinds of vegetables. So what is seasonality? If a predictable pattern that repeats itself at a certain frequency within a year or within a week or within a month or quarterly or within an hour also, then we will call it as a seasonal pattern. So you see the internet traffic time series. You know that in daytime, the internet traffic is high and in nighttime, the traffic is low. The traffic in our roads. So you see in daytime, the traffic is high, in nighttime, the traffic is low. So here it follows a seasonality for a period of a day, right? So apart from seasonality, if we are getting any other repetitions, which is more than 2 years, then we will call it as a cyclical component. So the cyclical component of a time series refers to regular or periodic fluctuations, excluding the irregular component. So you see cyclic components again repeats itself, but it is beyond the season, means beyond 1 or 2 years. Then we will call it as a cyclic component. And the fourth one is the irregular component. So you see, as we are predicting, we are always going to have some errors. Even though our model is very efficient, still we are going to get some errors. We can never model the irregular components. So this is the components that is unpredictable, right? So now let us go through what exactly time series forecasting is. So time series forecasting is the process of predicting the future outcomes of a phenomenon by systematically analyzing its past observations. For example, we have observed a time series from x1 to xn. If we want to predict xn plus h by analyzing x1 to xn, then it is called as time series forecasting. So here you see xn plus h is called as forecasting horizon. If h equal to 1, it means by analyzing x1 to xn, we will predict xn plus 1. This is called as one step ahead forecasting. And when h is more than 1, then that is called as multi-step ahead forecasting. So now you see one step ahead is pretty simple. x1 to xn we can take, and I will discuss how we will predict. But multi-step ahead forecasting can be done in two ways. One is direct multi-step ahead. Another one is recursive one step ahead. Direct multi-step ahead means by taking x1 to xn, we will suppose predict xn plus 5 directly without computing xn plus 1, n plus 2, n plus 3, and n plus 4. But in recursive multi-step ahead forecasting, what I will do, we will repeatedly do one step ahead forecasting. Means by taking x1 to xn, we will predict xn plus 1. Then by taking x1 to xn plus 1, we will predict xn plus 2. Then by taking x1 to xn plus 2, we will predict xn plus 3. Similarly, we can predict xn plus 5. But the recursive forecasting methods, multi-step ahead forecasting methods, has the drawback of correlation of errors. Means if there is an error in the prediction of xn plus 1, it will affect the prediction of xn plus 2. So let us go through another thing that is called as forecasting method. A forecasting method is a procedure to predict the future values by systematically analyzing the past observations. So the forecasting methods may be judgmental, univariate, and multivariate. Judgmental means, you see, every day we are doing forecasting. You see, whether while returning to home there will be rain or not. If there will be rain, we will take the umbrella, otherwise we will not take the umbrella. While traveling to the market, how the traffic is. So accordingly, we will plan our route, right? So every day we are making forecasts based on our own expertise in a particular domain, right? And when we are using expertise of a particular person, of an expert, then such kind of forecasts are called as judgmental forecast. Whereas in univariate forecast, we will analyze a single series. For example, suppose we want to predict the temperature. If I am analyzing the temperature time series of that particular area, and I am predicting the future temperature, then such kind of forecasting methods are called as univariate forecasting method, where a single variable is associated, right? Multivariate means multiple variables, means predict in order to predict a time series. In addition to the prediction series, we will consider some other explanatory series. For example, in order to predict the temperature, suppose we are considering temperature time series, we are considering pressure time series, we are considering humidity time series, then it becomes a multivariate time series forecasting. So in this presentation, I will specifically focus on univariate time series forecasting methods. And the univariate time series forecasting methods are particularly important if we do not know what are the explanatory variables that affect the prediction time series, then the univariate forecasting methods are particularly useful. For example, suppose we want to predict the crude oil price. Crude oil price is affected by many factors. For example, if there is a political change in the exporting countries or importing countries, then it will affect the crude oil price, right? If there is a war kind of situation, you see in Russia there is a war, so it affected the exporting Russia crude oil country, right? And those countries who are importing from Russia, they are also affected. So varieties of, if multiple factors are affecting a particular time series and we cannot correlate them, then it's better to use univariate time series forecasting methods. So the researchers always confuse between forecasting method and forecasting model. That's why I have put those two things in the slide. So what is a forecasting model? A forecasting model is a tool to reveal the relationship existing in the past data using which future values are predicted. For example, a forecasting model may be a statistical model like ARIMA, RFIMA, exponential smoothing, naive. However, these statistical models assume that the time series is generated from a linear process and often fail to provide satisfactory result if a time series is nonlinear. However, most of the real world time series are nonlinear and often suffered by temporal and spatial variability. So in order to capture the nonlinearity associated with the time series, nowadays nonlinear machine learning models, including deep learning models, are extensively used in time series forecasting. But you see, I have already gone through the basics of time series and time series forecasting without telling you why we will do time series forecasting. So you see, if by somehow you can predict the future, suppose you know that after completing my PhD, I will get a job in this company or in this university. So you see, accordingly, you will prepare, you can make your decisions, right? So if you will know that if the stock price of a particular stock is going to increase, then you will purchase that stock. If you will know that, or if you can predict the crude oil price, then you can make appropriate policies relating to crude oil purchasing or selling. If you know the particular demand of a product in a retail industry, then you can maintain appropriate inventory without over keeping the material or without under keeping that material, so that you can maximize the benefit. If you can predict the internet traffic, the service providers can provide better internet service. If you can predict the electricity load, you can purchase or sell electricity in the balancing market and you can have a better electricity supply. If you can predict the call volumes in a call center, so that accordingly you can schedule staff. If a particular time the call volumes are larger, then more number of staffs will be there to attend the calls, right? Similarly, if you can predict the disasters, natural disasters like flood, earthquake, tsunami, then you can make the mankind prepared for those events. So I have just named a few of the applications of time series forecasting, but looking into the perspective of this workshop, I have identified some of the applications for material engineers. So if you can predict the material properties like tensile strength, hardness, or conductivity of a material based on historical data, then you can control its quality and you can plan the production. If you can predict the lifetime of a material subjected to constant stress or cyclic loading conditions like aerospace components, it will assist planning, maintenance, and replacement accordingly. If you can predict the demand pattern, lead times, and optimal order of quantities, you can efficiently manage the inventory without keeping excess quantity or without keeping under quantity. If you can predict the behavior of electrode materials in battery concerning voltage behavior and other electrochemical properties over time, it will assist in designing and optimizing the energy storage system. If you can predict the expansion and contraction of materials subjected to various temperature conditions, it will assist you in designing components that can withstand temperature variation. If you can predict phase transformation and crystal growth, it will assist in designing the materials with specific properties. And another application of time series forecasting is failure prediction in composite materials. So composite materials are materials which build up multiple components. You may know better than me. So in those components, if you can predict when the delamination or fiber breakage and other type of failure is going to happen, then accordingly you can replace them and you can maintain them. If you can predict the environmental impact of materials over time, considering factors like emission, resource consumption, wastage generation, you can develop sustainable materials. So I have just listed a few of the applications of time series forecasting. But now the important thing is how you will perform time series forecasting, and especially by using deep learning models. Because you see nowadays, all the data in this internet and IoT era, all the data are captured at an interval of time. So a time component is associated with the data. So all are forming a time series. Now it's important how to analyze the time series efficiently. So as the time series are large scale, the deep learning models are more efficient than other shallow machine learning models. However, it is not always true. You have to test. OK, but let us see how you can do time series forecasting by using deep learning models. Suppose we are having a time series x1 to xn, and I want to predict xn plus 1, and I want to do it by using a deep learning model. So I have used a deep learning model with 6-7 number of layers and with varying number of neurons at each layer, right? And suppose by analyzing the autocorrelation and partial autocorrelation of the series, or by analyzing the recurrence quantification analysis of the series, I have identified that the future value is dependent on past 3 values. So what I will do? I will take x1 to x3 as input and I will set x4 as the target. Then I will move the window. So this procedure is called a sliding window, right? Then I will take x2, x3, x4 as input and I will set the target as x5. Then what I will do? I will set x3, x4, x5 as the input and I will set x6 as the target. So by this way, what I am doing, I am converting the time series, univariate time series into input and target patterns by using the sliding window technique. So you see, after converting the time series x1 to xn into input target patterns, I can determine the optimal architecture and other hyperparameters of deep learning model. Then if I will give xn minus 2, xn minus 1 and xn as input, whatever I will get as output, that will denote the xn plus 1 value. But here the big question is how to know the architecture and other hyperparameters of the deep learning model, because the performance of deep learning model is dependent on its architecture and other hyperparameters. Architecture means how many number of layers, how many number of neurons in each layer, what is the value of weights, what is the value of biases, what is the value of which activation function we will use, how to initialize the weights, whether I will use Hay initializer or Glorot initializer or any other initializer. What is the batch size? What is the dropout rate? What is the learning rate? What is the optimizer? So the big question is how many inputs, and the number of inputs can be analyzed, can be obtained by analyzing the autocorrelation and partial autocorrelation function of the series, or by making recurrence quantification analysis of the series. And how many layers? We will go through how to optimize these things. How many number of neurons in each layer? Which activation function? Which kernel initializer? Which optimizer? What is the base size? And what is the learning rate? So you see, in order to answer all these questions, we can have these three approaches. One can use a grid search or a Bayesian optimization, or they can use a swarm and evolutionary algorithm. But the grid search has a drawback that it is inappropriate to handle the continuous valued hyperparameters like learning rate, dropout rate, etc. So you see, in grid search, what we will do, we will give a set of values. Number of layers, we can set it as 3, 5, 7. We can give set of values. Activation function, sigmoid activation function, ReLU activation function, ILU activation function. But you see, if the hyperparameter contains a continuous value, for example, learning rate, so it can be any value between 0 to 1. So which set of value will you give? Okay. For example, dropout rate, it's any value between 0 to 1. So there is no set of values, right? So it cannot appropriately handle the continuous valued hyperparameter. And the second drawback of grid search is suffers from dimensionality issue. So if the number of hyperparameters are large, then grid search is not appropriate for optimizing the architecture and other hyperparameters of deep learning models. Then the second approach is Bayesian optimization. But the Bayesian optimization is more appropriate for continuous valued hyperparameters, but it cannot appropriately handle the discrete valued hyperparameters like activation function, kernel initializer, number of neurons in each layer, and it also suffers from dimensionality issues. Whereas, contrasting to grid search and Bayesian optimization, the swarm and evolutionary algorithms can handle both continuous valued attributes and discrete valued attributes. So you see, in deep learning model, we have continuous valued hyperparameters and we have discrete valued hyperparameters. So it suits to optimize the deep learning architecture and other hyperparameters. And the next thing it is scalable because it supports parallelism, right? So motivated from this, in the literature, in the last 5 years, some literature relating to optimization of deep learning models has been obtained, right? So they have used it to optimize the CNN convolutional neural network, LSTM, long short-term memory, deep neural network, recurrent neural network, deep belief network, and they have used these hyperparameters. I will share the slides. You can have a reference of this. OK, I have also listed the references in the reference so that you can go through it. And they have used evolutionary algorithm, particle swarm optimization, fractal decomposition algorithm, differential evolution algorithm. And you see here the key thing is how you will encode the deep learning hyperparameters into the chromosomes or into the decision vectors or into the position vectors. So it depends on the type of swarm and evolutionary algorithm you are using. But the important thing is how you are encoding. So the authors have used variable length, real encoding, block encoding, binary encoding, fixed length, real encoding, binary encoding, and your block encoding. So you see, so the problem in this literature is that they have considered these hyperparameters: number of neurons in each layer, activation function, learning rate, batch size, dropout rate, kernel initializer, that is the weight initialization scheme. But none of the papers have considered all these hyperparameters simultaneously. And the next thing is the authors have used fixed length encoding scheme and variable length encoding scheme. The fixed length encoding scheme has the drawback that it cannot encode deep learning models with varying layers and is not flexible. Whereas the variable length encoding scheme has the drawback that complex implementation and high computational overhead. And the fixed length encoding may be binary, real valued or block, or the variable length encoding may be binary or real encoded or block encoded. And they haven't optimized the number of layers. And in addition to this, they have applied that optimization algorithm for a specific type of deep learning model. Means either they have optimized only CNN or they have used only to optimize LSTM or deep belief network like this. But they haven't developed a generalized method that can be applicable to all kind of deep learning models. So in order to overcome this gap, we have developed one methodology to optimize both continuous and discrete valued hyperparameters of deep learning models. And this is still in the revision stage, and we have published a preprint in SSRN. You can go through it. I have shared you the link. Where what we have done, we have tried to overcome the limitations of the literature. We have considered the number of neurons in each layer as one hyperparameter, activation function, learning rate, batch size, dropout rate, kernel initializer. And we have also optimized the number of layers. Then we have proposed a fixed length real encoding scheme. You see, the real encoding scheme has the drawback that it is not flexible and it cannot model deep learning models with varying layers. But we have developed a fixed length real encoding scheme with pruning method in such a way that it has the simplicity of fixed length encoding and the flexibility of variable length encoding. I will discuss it. OK. And we have used one of the simplest optimization algorithms, that is differential evolution. And this method is so generic that it can be applicable to different deep learning models. And in this paper, we have optimized 5 deep learning models. So how to do it? So you see, for this, first, we have to divide the data into train, validation, and test set. Then we have to generate a population size of deep learning models with varying parameters. So we have encoded different deep learning models in the decision vectors or chromosomes or position vectors. Then what we have done? By using the train set and validation set, by using the train set, we have obtained the model parameters. And by using the validation set, we have obtained the fitness of each deep learning architecture. Then we have tested whether termination criteria is satisfied or not. If termination criteria is not satisfied, we have generated the next generation or next population by using the DE, means differential evolution, mutation, crossover and selection schemes. Then we have repeatedly applied the DE, mutation, crossover and selection schemes to generate the next generation of deep learning models until a termination criteria is satisfied. And when the termination criteria is satisfied, then the best chromosome or best decision vector or best position vector of the final generation is used as the optimal deep learning model with its hyperparameters. Now here the important thing is how we have encoded a deep learning model into a chromosome. Okay, so let us go through it. So for this, what we have done, you see, encoding a deep learning model to a chromosome. In genetic algorithm, you call it chromosome. In differential evolution, you call it as decision vector. In particle swarm optimization, you will call it as a position vector. So it varies, but the concept remains the same. Okay, so you see how we have encoded a deep learning model into the chromosomes or into a decision vector or a position vector. So first we have fixed the maximum number of hidden layers. Okay. So if there are n number of hidden layers, for each hidden layer, we have fixed 4 hyperparameters. That is number of neurons in that hidden layer, the activation function in that hidden layer, kernel initializer in that hidden layer, and dropout rate. So you see, first I have kept the 4 hyperparameters of hidden layer 1. Then I will keep the 4 hyperparameters of hidden layer 2. Similarly, we will keep the all the 4 hyperparameters up to n hidden layers. Then after that, we will keep the model hyperparameters, that is the learning rate and the batch size. Here we haven't kept the optimizer. We have fixed the optimizer as Adam optimizer because Adam is the most promising optimizer for to train a deep learning model, right? So here, what is our objective? We have to minimize the fitness function by using CI. CI means the chromosome. This chromosome denotes a what? It denotes a deep learning model, right? Means in the first hidden layer, how many number of neurons, what is the activation function, what is the kernel initializer, what is the dropout rate. In the second hidden layer neuron, what is the number of neurons, activation function, kernel initializer. Similarly, we will set up to n number of hidden layers, right? Subjected to each gene of the chromosome lies between a upper bound and lower bound. So here, what is fitness? Fitness is nothing but we have evaluated the validation error is the fitness function. So mean square error on the validation set denotes the fitness of a chromosome, right? Then here the important thing is, sir, you have encoded a deep learning model to a chromosome, but how you have decoded it means from the chromosome, how you have obtained the deep learning model. So you see number of neurons. So when you will, we have used a fixed length real encoding. Real encoding means if I will apply mutation and crossover and selection, then I will get a real number in every gene. So number of neurons cannot be a fraction. So what I will do, I will convert that real number or I will round it off, then I will get a integral value for the number of neurons. Now, how will I get the activation function? So you see, suppose I am using 4 activation functions. 0 means ReLU, 1 means sigmoid, 2 means 10H, otherwise it is LU activation function. So you see, for the activation function, the lower limit is 0 and the upper limit is 4. So you see, if I am getting a value 3.2 over here, then what I will do, I will round it up. 3.2 means it will become 3. 3 means what is the activation function? If it is 3, it will go to LU activation function. If it is 0, it will give you ReLU activation function. So this is how I have decoded from a chromosome to an activation function. The same thing can be done for your kernel initializer. So you see, we have used 4 kernel initializers: Glorod uniform, Glorod normal, Hey uniform, Hey normal. You can extend it up to your level. There is no problem. Based on the availability, you can extend it, right? Then if a decision variable is there, first you see in step number 1, I am rounding it off so that I can get an integral value. If the integral value is 0, then the kernel initialization will be chloroteniform. If it is 1, similarly, I can get the corresponding kernel initializer. Now you see, I have decoded the number of neurons, activation function, kernel initializer, and dropout rate. Dropout rate is a continuous valued attribute, so no need to round it off, right? So what do you have to do? You can simply use the value with the lower limit as 0 and upper limit as 1. So this is how we have decoded and encoded the deep learning model parameters into a chromosome and from a chromosome. Then how will you decode the entire deep learning model? For that, you see what we are doing. We are in step number 1, we are taking a empty deep learning model. Then we are in step number 2, we are adding an input layer. So input layer can be obtained from the number of features you have in your dataset, right? So in time series, we will compute the number of inputs by analyzing the autocorrelation and partial autocorrelation function of the series, or by you making recurrence quantification analysis. So first we will add the input layer. Then for each hidden layer a hyperparameter. So we have used 4 hyperparameter for each hidden layer. So what I am checking first, you see, first I am checking the 4th hyperparameter. What is the 4th hyperparameter? The 4th hyperparameter is dropout rate. So what dropout rate says? Dropout rate says how much percentage of neurons I am going to drop out of one training epoch. So if dropout rate is 1, it means what? 100% neurons I will drop. It means that layer itself is dropped. So here you see. So first I am checking if the dropout rate is not 1. If it is 1, then I will skip that layer. Okay, so initially suppose I have fixed the maximum number of hidden layers as 10, and out of 10 hidden layers, if 2 hidden layers dropout rate is 1, it means those 2 layers will be dropped and I will have 8 number of hidden layers. So similarly, based on the dropout rate, the number of layers in the deep learning model can vary. Now you see, if the dropout rate is not 1, then what I am doing, the first decision vector, that is the number of neurons, I am rounding it off and getting the number of neurons. Activation function, I have called the get activation function. So I will get the corresponding activation function. You see, in get activation function, what I am doing, I am rounding up the value. Then based on its 0, 1, 2, 3, I am getting a specified activation function. Similarly, in kernel initializer, I will call the kernel initializer function to get the appropriate kernel initializer. Then I will add a layer to the deep learning model with n number of neurons, and then here I have obtained AF as the activation function and KI is the kernel initializer and VI plus 4 is the dropout rate. So this is how I will go on adding one hidden layers to the deep learning model based on the chromosome values. Then finally, what I will do, I will add the output layer. So here you see in forecasting, usually we use the output. The output layer usually contains 1 neuron, right? So add a layer with 1 neuron and linear activation function. That is the output layer. So based on your problem, you can add that many number of neurons in the output layer. Then I have set the batch size. So you see, after the hidden layer parameters are decoded, you see I am having other hyperparameters. Means those are applicable for the entire deep learning model. So here I have chosen 2 hyperparameters. One is learning rate, another one is batch size. So you see learning rate is a value between 0 to 1. It is a continuous valued hyperparameter. So no need to do anything, simply use that. But batch size should be a power of 2. It can be 2, 4, 8, 16, 32, 64, 128, but it should be a power of 2 for optimization process. Okay, for optimization purpose. So what I have done here, you see, learning rate we have kept it as it is, whereas batch size, you see, we are taking 2 to the power round of VD, right? It means whatever the batch size chromosome will contain, let's say it contains 3.15. What is the round of value? It will be 3. So 2 to the power 3 will be how much? 8. So the batch size will be kept as 8. So now what I will do, I will compile the deep learning model with mean square error as the loss, Adam as the optimizer, with learning rate set to learning rate. Right? Then I will return the deep learning model. So this is how we have encoded the deep learning models into the chromosomes. Then from the chromosomes, we have decoded into a deep learning model. We have computed the fitness. Then we have applied demutation, crossover and selection operations to generate the next generation from the current generation. And the next generation is repeatedly generated until a termination criteria is satisfied. So you see, this loop continues until the termination criteria is satisfied. When the termination criteria is satisfied, the best chromosome or the best decision vector or best position vector will be decoded by using our decoding algorithm, and we will get the optimized hyperparameters and architecture of the deep learning model, and we will use it on the test set. Now, this is how we have optimized a deep learning model. Now, the question is how to perform time series forecasting by using this optimized deep learning model. So for this, what we will do, we will first identify the number of significant inputs K of the deep learning model by analyzing the autocorrelation and partial autocorrelation function of the series. Let's say the number of inputs we have identified as 10. Then what we will do? Then we will convert the time series into patterns, input target patterns. But before converting, we have to pre-process the time series. Pre-process the time series means we have to normalize the time series. Normalize means transforming the data from one range to a range between 0 to 1 or -1 to 1, so that it will be more suited to be operated by the deep learning models. Then treatment of trend component. Treatment of if a time series has a trend component increasing or decreasing, what we can do, we can take its first difference or second difference or third difference to treat that trend component. Then we can detrend it afterwards, but first we have to treat the trend component. Then we have to treat the seasonal components. If there is a seasonal component in your time series, then you can take the seasonal average of the time series. Then you can subtract the corresponding value from the corresponding seasonal average, right? So there are so many methods for normalization itself. 5 to 7 methods are there. Treatment of trend, there are 2 to 3 methods are there. Treatment of seasonality component itself a research, right? So you can use any method and you can use different methods to check the sensitivity of your model, right? Then after pre-processing the time series, you will transform the time series of length into n minus k patterns by using the sliding window technique. So I have shown you the sliding window technique. Then the patterns will be split into train, validation and test set. So by using the train and validation set, you can determine the deep learning model parameters. So here you see what you will do. You can use our or any of the literature available approach you can use, or you can propose your own approach to overcome the limitations that is existing in the literature, and you can optimize the deep learning model. Once the deep learning model is optimized, then you can predict the test data, right? Then after you have predicted the test set, you have to denormalize it, because you see you have normalized it, means you have transformed the scale from one range to another range. So in denormalization, you have to again scale it back to the original range. Then you have to detrend it if you have trended it, and you have to deseasonalize it if you have done the seasonal adjustment. Then you can get the true forecast and you can measure the forecasting accuracy. So you see, over the last or prior to last decade, the statistical models are extensively used, like ARIMA, ARFIMA, exponential smoothing for time series forecasting. However, these models assume that the time series is generated from a linear process. However, most of the real world time series are nonlinear and often contain temporal and spatial variability. That's why we have used in the last decade optimized machine learning and deep learning models to capture the nonlinear patterns well. However, most of the real world time series may not be purely linear or purely nonlinear. Rather, it contains a combination of linear and nonlinear components. And in that case, neither linear statistical models nor nonlinear machine learning and deep learning models can give you better result. You see, suppose I am having a time series. So this is the passenger time series, airline passenger time series. So you see, it has two components. One is the linear component, that is the increasing trend, and another one is a non-linear component. So you see, so linear models are more suitable for modeling linear time series, whereas non-linear models are more appropriate for modeling non-linear time series. But if your time series contains a combination of linear and non-linear patterns, then you have to use both, or you have to use a hybrid model by incorporating a linear model with a non-linear model. So based on this, nowadays, these hybrid models are extensively used in time series forecasting. So let us first go through one of the hybrid models, that is called as additive hybrid model. So in additive hybrid model, what you do, you first take a time series, then you apply a optimized statistical model. You see why I am telling you optimized statistical model. A statistical model can only capture the linear patterns well if the parameters of that statistical model is optimized for that particular time series. That's why I'm telling you optimized statistical model. So you can optimize the statistical models like ARIMA, your ARFIMA, or exponential smoothing ETS with error, trend, and seasonality component. And Sarima, all these models you can optimize by using forecast package of R. Just a few lines of code, 10 to 12 lines, it will give you the optimized statistical model for that particular time series. So after obtaining the optimal statistical model, you will get the forecast from the statistical model. Now what you will do, you see, you subtract the statistical model forecast from the original time series so that you will get the residual series. So here you see, let me go through the previous example. You see, this is the original time series and this is the linear component which can be modeled by a linear statistical model. Now, if I will subtract the linear component from the original time series, then what I will get? I will get this nonlinear component. So you see, first I have modeled the linear component using a linear statistical model. Then I have subtracted the linear forecast from the original time series so that I can get the residual series. Now you see the residual series is nonlinear. So as it is nonlinear, it will be modeled by using a nonlinear model. And the nonlinear model, if it is optimized for that particular residual series, then it will give you the better forecast. So now you will use a optimized machine learning or deep learning model to model the residual series. Then the final forecast can be obtained by adding the optimized statistical model forecast with the optimized deep learning model forecast, right? So contrasting to this additive hybrid model, one can use a multiplicative hybrid model. So in multiplicative hybrid model, what you will do, you see, you will first take a time series, you will model it or apply a linear statistical model to it. You can optimize that model, then you can apply it. Then instead of subtracting it from the original time series, what you will do, the statistical model forecast will be divided from the original time series to obtain the residual series. So here you see, here the time series is not an addition of linear and nonlinear component. Rather, it is a multiplication of linear and nonlinear component. So instead of subtracting it, you will divide the linear component to obtain the nonlinear residual component. Then once the nonlinear residual component is obtained, you can use, you can again apply the time series forecasting methods, like you can convert it into or you can convert it into input target patterns by using sliding window. Then you can model the input target patterns by using optimized machine learning and deep learning model. models, and the final forecast you can obtain by multiplying the optimized statistical model forecasts with optimized deep learning model forecasts. But here you see, while applying this multiplicative hybrid model, you need to take care of one thing. What is that? If the denominator is 0, if the statistical model forecast is 0, then you see you will get a divide by 0 exception. So in order to handle it, what you can do, if the statistical model forecast is 0, you set a small value, let's say divide it by 0.1 or 0.01, right? So it will hardly affect the accuracy, but it will avoid the divide by 0 error. So contrasting to this series hybrid models. So here you see, in the series hybrid model may be additive or it may be multiplicative. In series hybrid models, what we have done? We have directly applied a statistical model on the time series and we have obtained the linear forecasts. Then we have subtracted the linear component forecasted values from the original time series to get the residual series. However, you see, applying a statistical model which is linear to a time series which contains a combination of linear and non-linear patterns is not appropriate. So for that, what you can do, you can use parallel hybrid models. So you see, is your ARIMA linear statistical model ARIMA can give better result if the time series is truly Gaussian, right? So if your time series contains a combination of linear and non-linear patterns, it will not satisfy that Gaussian property and it might not be stationary also, right? So in that case, these hybrid models will give poor results, right? So in order to overcome this, we can use parallel hybrid models. So in parallel hybrid models, what we will do, you see, instead of applying a single model to the original time series, we will apply multiple models to the same time series. So you see here the same time series is given as the input to multiple machine learning, deep learning, or even you can take statistical models. Then what you will do, you can get individual forecasts. Model 1 forecast, model 2 forecast, model n forecast. Then you can compute a weighted summation. So here you see the weights can be of equal weight. Equal weight means, let's say you are n models you are using. The final forecast you can obtain by adding all the model forecast and dividing by n. So here you see, if you will take the mean of the forecast, then the weight of each forecasting model is same. But contrasting to this, you can have equal weight parallel hybrid models. You can have variable weight parallel hybrid models. Variable weight means, you see, to this model, let's say you are giving 0.2 weight, 0.2 into F1, 0.3 into F2, let's say 0.5 into F3. Okay, so here you see the weights to the forecast combination differs. So if the weights are different, if weight are same, then it's simple. Take the average of all the forecasts, right? But if the weights are different, how to know what weight to give to each individual model? So for that, what you can do, you can compute the forecast on the train set. Then in order to get the weight for each forecast, you can use a gradient descent method or you can use a swarm and evolutionary algorithm to obtain the optimal weights of the combination. So if you want to use a swarm and evolutionary algorithm, then what you will do? You will encode the weights as the genes of the chromosomes, or you can encode the weights as the decision variables of the decision vector. Next, what is your fitness? In that case, the fitness will be the train error. Root mean square error on train set means on train set you will compute the forecast, you will compute the ensemble forecast, then you have the actual forecasts, actual values, then you compute the error between them. Okay, squared error. So your fitness should be the squared error between the ensemble forecast and the actual values. Okay, and your objective is to minimize the sum squared loss. Okay, like this way you can develop a variable weight parallel hybrid model. So contrasting to this variable weight, in this variable weight, what do? We give the same variable weight to different time instances. For example, here you see, here let me take a time series, let's say 5, 7, 9, 3. This is the, let's say, original time series. And let me take, this is the forecast 1. So in forecast 1, suppose we are getting 4, 6, 8, 4. In forecast 2, let's say we are getting 3, 8, 5, and 6. So now you see, suppose we have got two parallel models we have used. And let's say the weight of this one, is, suppose we are giving 0.9 weight to this model forecast, and we are giving 0.1 weight to this model forecast. So you see here how we will compute the forecast. So 0.9 into 4 plus 0.1 into 3. This will be the forecast of the parallel hybrid model. And for this one, what will be the forecast? 0.6 into 9.9. Sorry, 6 into 0.9 plus 8 into 0.1. But here you see, at different time instance, we are giving the same weight. Although the weights are different, but we are using the same variable weight at different time instance. So what the researchers have thought, why not give time varying weight? Time varying weight means in this time, it will give the weight as 0.9 and 0.1. Whereas in the next time, it will give the weight as 0.8 and 0.2. So I hope all of you have understood what I mean by time varying weight. Means based on time, we are varying the weight of the ensemble. Okay, so this can be achieved, or time varying weight ensemble forecast can be achieved by using either Kalman filter or by using your hidden Markov models, right? So you can use them. So here you see in this parallel hybrid model, what we have done? We have directly applied the original time series on multiple models. Then we have assembled the forecast to obtain the final forecast. However, in decomposition based hybrid models, what we will do, you see, in decomposition based hybrid models, what we will do, we will first decompose the time series into n components by using either empirical wavelet transform, or these are signal processing techniques, empirical mode decomposition or empirical ensemble mode decomposition, complete ensemble empirical mode decomposition with adaptive noise, or variational mode decomposition. Then on the individual components, those are called as intrinsic mode functions, we will optimize the deep learning or machine learning models. Then we can combine the forecast of different models on the individual intrinsic mode functions to get the original forecast, right? So you can use this decomposition based hybrid models, and authors have used also what, based on the time series model. So the time series has components trend, seasonal, cyclical, and error, right? Or residual. So you see, one can decompose the original time series. This observed means the original time series, right? One can decompose this observed time series into three components. One is trend, another one is seasonal, another one is the remaining, that is the residual components. Means this is the how you will get this: observed minus trend minus seasonal. Then you will get the residual component, right? So this is how you can get the residual component. So what you will do after decomposing the time series into trend, seasonal, and residual component, you can optimize models for individual trend, seasonal, and residual component. Then you can combine the forecast, right? So these are all about your decomposition based hybrid models. So now whatever I have discussed till now, these all are crisp time series forecasting models. Crisp time series forecasting models means the time series data are from a real domain, right? So now you see what you can do, sir. We can convert a time series into crisp time series into a fuzzy time series. How can you convert? For example, let me take a temperature time series. So temperature time series, let's say the temperatures are 10.2 degrees centigrade. Then I can take 15 point, let's say the temperatures are like this, 15.3. Then let's say it is 20.4, right? Then let's say 38.2. Okay. So now what you can do, suppose you have identify the intervals. Let's say 5 degree to 15 degree is very low. So what you can do, you can replace it with very low. 15 degree to 20 degree, 25 degree is low. So you can name it as low temperature. This is low temperature. 25 to 35 is medium. So you can name it as medium temperature, right? So you can define different sets, okay? Different sets for each interval. And you see 15.3 is low temperature, but you see it is belonging to low by just a margin of 0.3, right? So what I will do, we will assign a membership to this set low, that is 0.9, and we will assign a membership to very low with a membership of 0.2, sorry 0.1, and we will assign a membership of medium with a membership of 0. So now what do you see? We will convert this crisp time series to fuzzy time series, means we will use linguistic terms, okay, to represent the crisp time series. Then what I will do, we operate on fuzzy domain, then we will predict. How we will do, I will tell you. But this is how we do fuzzy time series forecasting, okay? So you see in fuzzy time series forecasting, first what I will do, the universe of discourse of the time series will be determined. Universe of discourse means, let's say the temperature, minimum temperature is 5 degree, the maximum temperature is 45 degree. So what I will do, in future, we might have a temperature which is low, less than 5 degree, and which might be more than 45 degree. So what I will do, we let's say we will subtract 5 from this and we will get 0 is the lower limit of the universe of discourse and 50 is the higher limit of the universe of the discourse, right? So the universe of discourse defines the set of all possible values that a set might have, right? So for a time series, we will define the universe of discourse by taking a practical increment on the higher value and a practical decrement on the lower value. Then what I will do, we will divide the universe of discourse into number of intervals. So you see, now the universe of discourse is from 0 to 50. So we will divide it into, let's say, 5 intervals. 0 to 10 degrees, very low temperature. 10 to 20 is low temperature. 20 to 30 medium temperature. 30 to 40 high temperature. 40 to 50 is very high temperature. Now what we have to do, we have to fuzzyfy the time series. So first step is define the universe of discourse and split the universe of discourse into number of intervals. But here you see, I have splitted the universe of discourse into equal number of intervals or equal length intervals. Equal length intervals means 0 to 10, the length is 10. 10 to 20, length is 10. 20 to 30, length is 10. 30 to 40, length is 10. But what the authors have done, the researchers have done that. No, why to take equal length intervals? Let us take variable length intervals. Variable length interval means 0 to 15, low temperature. 15 to 20 or 0 to 15, very low temperature. 15 to 20, low temperature. 20 to 27 medium temperature, 27 to 35 high temperature, right? So you see, you can divide the universe of discourse into equal length intervals or variable length intervals. Okay, and you see, the interval should be chosen appropriately. If the intervals is too high, let's say you have taken that 0 to 25 low temperature, 25 to 30 is high temperature. So you see, your prediction accuracy will not be that much great, right? But if you have divided into so many intervals, let's say suppose interval length is what? Suppose you have defined 50 fuzzy sets to denote the temperature. Then you see it again becomes to crisp domain. The fuzziness will vanish, right? So the length of the interval is a crucial parameter. So after determination of the length of the interval, you have to fuzzify the time series. So in order to fuzzify the time series, what you will do, exchange each observation of the time series by the index belonging to the belonging interval of the observation. For example, you see, excuse me, suppose the temperature is 22.3 degrees centigrade. So what you will do, it belongs to each interval 20 to 30. So what is the index? So 0 to 10, the interval index is, let's say, 0. Then 10 to 20, the interval index is 1. 20 to 30, the interval index is 2. Then 30 to 40, the interval index is 3. 40 to 50, the interval index is 4. Now you see 22.3 is an observation. So you will replace it with 2. So now you see, if you will replace each observation by the interval index, then what you will get? You will get the time series in terms of linguistic variables, right? Then what you can do, here we are not considering the membership values. Even we are not computing the membership values, but there is another method for considering the membership value that I will go. Okay. So after converting the time series into interval indexes or fuzzy time series, what we will do, we will apply the same time series forecasting method. Now we will determine the number of inputs by analyzing the autocorrelation and partial autocorrelation function of the fuzzy time series. Then we will establish the fuzzy logical relationship. Fuzzy logical relationship means suppose the input is dependent on past 3 values. So I will use a sliding window technique to convert the fuzzy time series into a input output pattern, and that we are terming it as fuzzy logical relationships. Then those fuzzy logical relationships or input target patterns will be modeled by using a ML or DL, machine learning or deep learning model. Now, after modeling the fuzzy logical relationships, what we can get? We can get the predictions on test set. But the predictions on test set will be what? Will be the interval indexes. So what do we have to do? We have to again defuzzify it. Defuzzify it means from interval index, again we have to take it to the original domain. How will you take? If our prediction value is 4. So the temperature will not be 4. The temperature lies in the 4th interval. So 4 means the range is 40 to 50. So what you can do, you can compute the midpoint of this interval, that is 45. So you can replace 4 by 45 degrees centigrade. That's why I have told you, if the length of the interval is too large, then while taking the mid value, you might get more error, right? And if the length of interval is too small, then you will lose the usefulness of fuzzy set, right? So while designing the fuzzy time series forecasting methods, these factors you need to take care. One is partitioning of universe of discourse. It can be done by using either equal length partitioning methods or variable length partitioning methods. Equal length partitioning methods are average based, modified average, ratio based methods. And variable length partitioning methods are cumulative probability distribution approach using swarm and evolutionary algorithms and fuzzy Siemens clustering. Due to lack of time, I am not focusing on this, on each aspect of this, but we have used all these things. And then the modeling the fuzzy time series for fuzzy logical relationships. So traditionally the rule based methods are used. Rule based methods means if the antecedent is this, the consequent is this. If the antecedent is this, the consequent is this. You have to define fuzzy rules and based on that you have to take decisions, right? So instead of that, nowadays the machine learning, deep learning, and even the hybrid models what I have discussed are used to model the fuzzy logical relationships and to predict the future values. Next, of course, you can take different fuzzification and defuzzification methods. You can take different fuzzy sets. So I have worked on traditional fuzzy set, neutrophobic fuzzy set, hesitant fuzzy set, and intuitionistic fuzzy sets for developing fuzzy time series forecasting methods. Then you can consider or you may ignore the membership values. So this approach what I have told you here, we haven't considered the membership values. But after this, I will tell you another approach where we will consider the membership values. Then the type of membership function, if you are considering the membership values, how you are computing the membership values, whether you are using a triangular membership function or you are using a trapezoidal membership function, are you optimizing the parameters of triangular and trapezoidal membership functions or not? Okay, so those factors will come into action. Okay, so now here this is a fuzzy time series forecasting method using deep learning models, and here we will consider the membership values. So what I will do, you see, first we will consider a time series. Okay, then we will normalize the time series. Then we will fuzzify the time series, means transform it into fuzzy domain. Then we will compute the membership of each member to each of the fuzzy sets. And you see here what I have done, I have written mean of membership values. It means I am not considering all the membership values of a particular element to all the fuzzy sets. I am considering the mean average of that. Okay, why? You see, if I am having 20 fuzzy sets, so for each element, if I will use 20 membership values along with the original value, then you just imagine that if the input is, let's say 100, then 100 plus 100, 100 inputs plus 20 into 100 inputs. That will be the input dimension. So the complexity of the model will be drastically increased. So in order to make the model simplified, instead of considering all membership values, we have considered the mean of the membership values. So still we can have the membership values fragments along with the original data elements. Then what we are doing, you see, we are converting the fuzzified data into patterns, that is input target pattern, by analyzing the autocorrelation and partial autocorrelation function. Then based on that number of inputs, we will transform the membership values into input and target patterns, right? Then this fuzzified data pattern will be modeled by using a optimized deep learning model, and the membership pattern will be modeled by using a optimized deep learning model. Then we will extract deep features from the optimized deep learning model and this optimized deep learning model. Then we will horizontally stack them. Okay. So once we will horizontally stack them, what we will have? We will first have the, so here we will horizontally stack them, right? So first we will have the data pattern deep features, then we will have the membership function deep pattern deep features, right? Then we will use a machine learning model on those deep features to forecast the future value. But you see, the forecasted value is a normalized and a fuzzified value. So what we have to do? We have to denormalize it, we have to defuzzify it, then we have to measure the forecasting accuracy. Right? So now you see what we can do. you can consider, or what I have done, I am sharing my experience. I have used traditional fuzzy set. In traditional fuzzy set, what do you use? We use the membership value. We may use membership value or we may ignore the membership value. Two approaches are there. Suppose we are considering the membership value. Membership value means, suppose I will ask you tomorrow whether what is the membership that tomorrow's day will be a rainy day. Suppose you are telling that yes, today is raining, yesterday also rained, and tomorrow, sir, the membership value is 0.7. So in traditional fuzzy set, we are just considering the membership value. Whereas in intuitonistic fuzzy set, what we are considering? We are considering the membership value as well as non-membership value. So now here the importance is, you see. So if I am considering the membership value, tomorrow will be a rainy day is 0.7. The non-membership value tomorrow will not be a rainy day. You might think that sir 0.3, 0.7 plus 0.3, it's 1. Yes, if you are deterministic, means if you are sure that tomorrow it will rain 0.7, it will not rain 0.3, then you can say like that. But you see, suppose you are confused, you also don't know whether tomorrow will rain or not. So what you may say, sir, tomorrow it will rain 0.7. If I will ask you tomorrow it will not rain, sir, 0.2. Or what is the membership to a non-rainy day? So you may say that 0.2. So you see 0.7 is membership, 0.2 is non-membership, whereas 0.1 is the hesitancy. Means you also don't know whether tomorrow will be a rainy day or tomorrow will be a non-rainy day, right? Means you are having that much of hesitance, right? So in traditional fuzzy set, we are considering only membership value, right? Whereas in intuitonistic fuzzy set, we will compute the membership value, we will compute the non-membership value, then we will get the aggregate intuitonistic fuzzy element by aggregating the membership and the non-membership value to represent a common membership value, right? Whereas in case of hesitant fuzzy set, we will consider the membership value, non-membership value, and the hesitation value, right? And here the important thing is, here it is the membership, non-membership, and hesitation are dependent values. Dependent means the sum of membership, non-membership, and hesitation should be equal to 1. Whereas in case of neutrophobic fuzzy set, it is independent. Thus, membership may be between 0 to 1, the non-membership may be between 0 to 1, and the hesitation also may be between 0 to 1. So considering all these things, if I will tell you the big picture relating to time series forecasting, you see, so I have just told you regarding univariate time series forecasting. There is another big story relating to multivariate time series forecasting, which I haven't focused in today's session. Okay, so you see, time series forecasting can be univariate or multivariate. I am not focusing on judgmental, right? So univariate can again be crisp or it can be fuzzy. So in CRISP, you can use individual models like statistical or machine learning or deep learning models. Individual means one model, right? So you can optimize it. You can optimize the machine learning, deep learning model. You can do, or you can use hybrid models. So these hybrid models may be series or it may be parallel, right? So series hybrid models may be additive or it may be multiplicative. Similarly, the parallel hybrid models may be equal weight, variable weight, time varying weight, or it can be of decomposition based. Decomposition based is again EWT, then EMD, VMD, EEMD, CEMDN, or you can use STL decomposition, right? Next, coming to the fuzzy set. You can use traditional fuzzy set, intuitonistic fuzzy set, hesitant fuzzy set, neutrophobic fuzzy set, type 2 fuzzy set, picture fuzzy set. The authors are using, but I have used this for, that's why I have mentioned, right? And this I haven't referred. Based on my research, I have tried to draw a picture like this, and I want to share it. And in traditional fuzzy set, you can ignore the membership or you can consider the membership, right? And based on all these things, we have published some papers. So these are the papers that we have published based on crisp time series forecasting, right? And these are the papers we have published based on fuzzy time series forecasting. Here the first paper employs traditional fuzzy set without considering membership value, whereas that second paper uses traditional fuzzy set by using the membership value. So here the complexity will be more. And here the third paper we have considered intutonic fuzzy set. You can refer to these papers. Okay, I have said you the link. Okay. Then in the fourth one, we have used neutrosophic fuzzy set. In the fifth one, we have used hesitant fuzzy set, right? And based on this time series forecasting only, okay, I have got these three projects from SERB, Government of India, that is studies on deep learning models for crude oil price forecasting. So the paper, what I have shown you and what I have explained, the optimizing deep learning models and using it for crude oil price forecasting is from this SERB project. And the second one that is completed recently, design and development of large scale time series forecasting methods using deep learning model. This is from Odisha State Higher Education Council. And through this project, I have developed an electricity load forecasting software for Western Odisha that is presently being used by TPWDL to forecast the next 2 days electricity load, that is electricity consumption, so that accordingly if there is a deficit they can purchase it from other grids, and if there is a surplus then they can sell it to other grids. And the another project I have sanctioned, but till date I haven't started this project. This is a consultancy project from Hindalco to predict the pot temperature. Means the pot where the bauxites are converted into alumina. So a certain range of temperature need to be maintained in that pot. So my job is to predict whether the temperature will be more than that or it will be less than that. So if it will be more than, then they will take some necessary action so that it will come down to that range, or it will be less, they will add something so that it will go to that range. Okay. So these are the references that you can refer. All these references are based on optimization of deep learning models. You can refer it, you can use it. OK, thank you for your valuable time. Now I expect some questions. If you have any questions, please.
Yeah. Thank you, sir. Thank you so much for your wonderful talk on this time series forecasting methods. So now I welcome participants. So who are having doubts, please raise your hands. We will unmute you.
Hello, am I audible, sir?
Yes, yes, audible. Please continue.
Yes, yes, sir. I have one question. Sir, how we
Yes.
design and predict the mechanical properties like strength, elongation, hardness based on the certain input variable? Suppose I have 100 data points like
Yes.
chemical composition, hot rolling, cold rolling reduction, annealing temperature, time. So how we predict the mechanical properties based on various machine learning model? And the most important thing is how we get the code to run the program.
How will you get the code?
Yes, sir, to run the program. Because I'm in mechanical background, so I don't know how to get the code to run the program.
Okay, you see nowadays code is pretty simple. You can refer it from the internet also. In GitHub, most of the codes are available. But before that, you need to know the basics of machine learning. So here, coming to your problem is a multivariable forecasting problem, right? Means you are having multiple features. Based on
Yes, sir.
that, you have to predict a particular value. For that, what you can do, you first let me go through the multivariate time series forecasting things. You see what you can do. Yes. So if it is a multivariate program, you can directly you can pre-process the data, means normalize to its range. Then you can directly apply the machine learning and deep learning models to get the output, right? So you see you have the data. So you split it into three parts: train, validation, and test.
Yes, sir.
This is okay. So this is train. Then you can have validation and you can have test, right? So based on the train and validation data, you optimize the deep learning or machine learning parameters. Then on test set, you can check which model is giving better result for the on-scene data. That is one thing. Another thing, so you can use FE. FE means feature engineering, right? Suppose you are having 5 features, 5 dependent variables, sorry, 5 independent variables. So what you can do, you can extract new features from these independent variables. It means, you see, you can give these 5 independent variables as an input to the deep learning model. Okay. Deep learning model, then you can set the target as your dependent variable, right? Then from any of the layer, by using train set, you can get the parameters of the deep learning model. Then on test set, when you are giving the inputs, you extract the features from the any of the layers. Then by taking those features and the target Y, you apply another shallow machine learning model on top of that, so that you might get better result. So this is one kind of feature engineering using deep learning models. Or you can take sign of the feature. Suppose you are having 5 features, then by taking 5 features, then you are taking sign of these 5 features. Okay, then you will get 10 features, right? Sign of these 5 features. Then you can also take cos of these 5 features, right? Then what you can do, you can take square of these 5 features. So similarly, you can expand the number of features, right? That is one thing. Suppose in the opposite case, suppose you are 100 features, you don't know which features are more appropriate for your problem. Then you can use a feature selection method. So feature selection method may be wrapper, maybe your embedded. Okay, so you can use those methods to select the subset of features from these out of these 100 set of features. And another one is dimensionality reduction. You can reduce the number of features and transform the features into another space by using your principal component analysis or linear discriminant analysis or independent component analysis, like dimensionality reduction techniques. Then after doing either feature engineering or dimensionality reduction or feature selection, whatever features you are getting, then you apply a machine learning and deep learning model on those features, right? I hope I have answered your question. Any doubt?
Yes, sir. Yes, sir. Thank you, sir.
Okay. Any other questions?
Sir, I think there is no more questions. So thank you, sir. Thank you so much for your valuable time to sharing your knowledge to our audience. Thank you, sir. Thank you so much.
Thank you very much for all of your time. Thank you. I'm leaving, Occur.
Yeah, okay, sir. Thank you.